let's talk about these different kinds of particles and what they mean to us. Basically, how we relate to these is radioactivity. That's what they are. They're what is left over after radioactive decay. Well, what is radioactive decay? Well, let me take some. There is an element called americium. There's its symbol. It has 241 nucleons. We won't worry about the protons in this case because we'll deal with this in the next lecture. Americium will decay into neptunium, which is itself pretty radioactive. 237 nucleons, and by doing that, it emits a helium nucleus, an alpha particle. Okay, so this is called alpha decay. This is alpha decay. So guess what beta decay is? It's when it emits an electron. Usually in beta decay, it emits an electron because you're converting a neutron into a proton in some form or other. Just so you have that general picture in mind, plus another kind of particle that we're not going to really worry about at this point. We'll talk about all the different kinds of particles there are and how they relate to one another and everything when we talk about topic 7.3. All right, so there's what a decay looks like, and it's because this happens because you have, remember we talked about coulombic forces versus the strong force in the nucleus of an atom. The coulombic forces want to push everything apart, but the strong force wants to hold everything together, but the strong force acts in a very narrow, very tiny space. And so when you get too many protons together, the coulombic force eventually takes over because the protons on the outer edge are outside of the effective range of the strong force. So neutrons are introduced, and they have no charge, so they don't suffer from coulombic forces, and they add to the strong force to try to hold things together. But eventually, you get so far apart, you have to add in so many neutrons that the nucleus becomes weaker and weaker and weaker and does not want to hold together. And this chart here shows this process up until about element 20. You have basically a 1-to-1 ratio of neutrons to protons. After that, you start gaining more and more and more neutrons until you have way more neutrons than you have protons, and it just all becomes kind of ridiculous, and nothing wants to stay together because the coulombic force is able to overcome the strong nuclear force just by sheer numbers and distance. Okay. All right, so americium is one of those, americium, I call it americium, is one of those elements that just wants to spontaneously fall apart because its nucleus is just too big to hold together. And so it does so by alpha decay. Now eventually neptunium is going to decay too because it's also too big, and it will do some kind of decay at the same time. All right, but what we want to talk about is something different. We want to talk about what they noticed as these things came out through the magnetic field. They noticed that an alpha particle, just come up here, an alpha particle has 5 megaelectron electron volts of energy when it's released. Okay, so that's joules of energy. Okay, that's a lot of energy that it's coming out with. And take that into consideration when you realize it only takes 10 electron volts to dislodge an electron from its orbit, and its orbital. So one of these things can ionize. The word is ionize because you're getting rid of electrons and you're turning things into ionized. So it's ionizing. It can ionize thousands, millions of atoms. We call this, in colloquial terms, layman's terms, burning. This is the process of burning. Okay, so when you get hit by alpha particles, they are ionizing your molecules and they are burning you. If you look at the PowerPoint that goes along with this, you'll see lots and lots, well, not lots and lots, you'll see poor people that were exposed to radiation and the humongous blisters that they have and things. That's because they burned. They were burned. They were ionized. So that's the process here. So let's see. So this is an interesting concept here, that there's energy that these come off with. This, let me make sure I've got my notes here. Yeah. Yeah, okay. So it comes off with 5 mega electron volts of energy. Now, when there is beta decay, so let's look at something like this. Carbon 14. So there's, carbon is normally 12 nucleons, so there's 2 extra neutrons here. Carbon pretty much wants to get rid of those. And so it will go through beta decay by emitting electron plus this particle. It's a neutrino, called a neutrino. And I'll talk about that in just a second. There's also such a thing, this is negative decay. There's also such a thing as positive decay. Now look, 10, it doesn't like that. So carbon does not want to have just 10 nucleons. So it will convert itself into boron by emitting what's called a positron or an anti-electron plus plus some kind of neutrino. Okay, we'll talk about exactly what these are much later, another lecture. That's called beta positive decay. So if you see the positive, that means it's a positron or an anti-electron. If it's negative, it's an electron. Okay, but what they noticed was that these electrons came off, or anti-electrons came off with a different energy. Kinetic energy was variable, whereas the energy for these were always 5 mega electron volts for the alpha particles. So beta particles was variable. Alpha particles was always constant, 5 mega electron volts. And so I thought, what would cause this? Why would this be? Well, that's where the neutrinos came in. They took some of the momentum because these were variable and they came off slower than were expected, something had to be taking their momentum. The energy, and we'll go into the energy calculations at another time, but the energy calculations showed that what went in was not what came out. That does not follow the conservation of energy and mass. So they had to introduce a particle that would help with that that problem. So okay, some of the momentum that the electrons are coming off of the nucleus is taken over by some of this other particle. So the electrons give up some of their momentum to these other particles as they're coming off. So that would equal the energy, mass, and energy conservation on both sides of these by doing this process. So that's where neutrinos came from, and they have been found. So they have been confirmed to exist, and this is the exact process that they go through. All right, so let's talk about gamma radiation. And so gamma radiation, let's take, I think this is polonium. This is a really nasty element, very highly radioactive, because it's got way more, it's way high on that chart. It's got way more neutrons than protons. And it will decay into another highly radioactive version of itself. So it's not done when it's done, when it goes through this process, plus a gamma ray. Now, you know how we have the discrete energy levels for electrons in orbitals, which we discussed. We also have discrete energy levels of energy for nuclei. They will absorb and emit certain wavelengths of energy. It's just that they're not in the visible light range around that narrow area. These are all in the gamma range, and this gamma radiation is very nasty stuff. It's very high energy radiation, and there is no surviving it. There is no mutating into Spider-Man or anything like that. So you will suffer greatly and quickly at the gamma radiation. So these are very high energy, short wavelength, high frequency electromagnetic radiation emissions. So an example of this, let's see, do I have an example of this? So that is an example of that. Now this will again decay into something else using one or the other of the different emissions, using either alpha, beta, or gamma. These are the particles associated with decay, radiation decay. All right. All right, so the higher up the periodic table you go, the less stable the nuclei are because of Coulombic forces versus the strong nuclear forces and the spacing that they're effective at. And so you get different kinds of decay. The three kinds are alpha, beta, and gamma. And you may have beta positive or beta negative, depending on whether it's a anti-electron or an depending on whether it's an anti-electron or an electron that is emitted. So one of the things, as they were studying, excuse me, studying this decay process, was that there was no way to tell. The decay process was not steady when you looked at it in an instance. You know, if you looked at it this second, you may have one nucleus decay. The next second you may have 5. The next second you may have 0. It was all random. You couldn't tell which nucleus was going to decay. You couldn't tell when it was going to decay. But they did notice that over time, it was a steady rate of decay, and it was an exponential decay. What they found was that, let me draw a chart here. Let me make my current layer visible. Okay, draw a chart to represent this. So here we'll represent this with the amount of material, some kind of radioactive material, something that spontaneously decays over time, and we'll put the time it's decaying here. Okay, so let me represent the first measurement at, we'll say this is time 0 right here. And that represents the amount of material that there was. Now, a certain amount of time later, there will be half of that. And then a certain amount of time, the same amount of time after that, half of that. And then half. And then you can see that this is an exponential curve. Not curved too well there, sorry about that. But you can see it's an exponential curve. And the time it takes to go to take a half, and this is not a half, but oh well, is called the half-life, and it's represented by T sub half. That's the time it takes for half of the material to decay. What they noticed, let me give you, well, yeah, let me say this. They noticed that the activity, it's called activity, is proportional. This is just something that they have come up with to give us a standard, is proportional to what the original population was. Now, activity is basically given in becquerels or BQ, and is the number of decays per second. Now, this is different than the half-life, which is the tells you the time to decay 1/2 of your population. Okay, so that is, but you can convert from half-life to becquerels or becquerels to half-life if you know the amount, the grams or kilograms or micrograms or whatever you have of your material. You can then convert this, because decays per second is really just an average of the half-life. If you think about this, it's an average based on the half-life, because even though we can't tell second by second how many exact decays there will be, over a half-life, a certain number per second had to average their decay, right? You had to have an average number of decays per second to get a half-life. So you can convert to that. All right, so one of the big things that IB will want you to do is to figure out half-lives. Now, how many half-lives does something take? And I don't know if you can hear my cat in the background, but she's kind of upset that she's being ignored right now, but oh well. So let's look at how to figure out how many half-lives something has. We have a kind of a formula that you can basically just come up with this in your head. You have your original population over one half-life. Half of that will decay, so you'll have half of your original population. Over another half-life, half of this population will decay, and so you'll have 1/4 of your original population. Another half-life will be half of that one, so it'll be 1/8, 1/16, and you see how this is going, right? Go on down. I've seen IB go down to 1/32, and then on and on like that. So that is basically your formula. Because let's take a problem here. Let's say we have radioactive isotope X, and it decays, and at time 0 we have 16 grams. At time 80 minutes we only have 1 gram left. So what is the half-life of this? Pretty easy to do. We write this out. We write this out. And at time 0, we have 16 grams. Then its first half-life, we have 18. We have 4, 2, and 1. So this took us 1, 2, 3, 4 half-lives. Okay, so 4 half-lives. So 4 half-lives in 80 minutes. So 80 minutes divided by 4 half-lives equals 20 minutes per half-life. So that means each half-life is 20 minutes, right? So T half equals 20 minutes. All right, so we've got a nice little formula here that we can use. This is T half, this is time, and this is number of half-lives. So T half, and this is not a formula in your book. This is something that you can use if you want to, or else you can just figure it out as you go along on your own. But if you understand this equation, it'll speed up your time just a little bit. So T, the half-life, equals the time over the number of half-lives. So if you know 2 of these, you can figure out the other one. If you have number of half-lives and you know the half-life of that element, you can figure out how long it'll take to go through that number of half-lives. You can figure out, as we did, the half-life of them, or you can figure out the number of half-lives given the time and knowing the half-life. So this is a very good equation to know. Okay, so that is the how to figure out the number of half-lives, what the half-lives are, how they represent, and so forth. So I just want to show you this one last table. Don't worry, you don't have to know it all. I can't get the whole thing on here, but let's see if I can. There we go. All right, so this table, you don't have to know anything about this table. I'm just putting it up here for general interest.